Okay, 3-2 is not a lot different. It's whether or not you can find a derivative. The word for being able to find a derivative is differentiability. So you have to know this word. Actually, it's differentiable. So we have to know this word. Because on the exam, that's exactly what they're going to tell you. They're going to tell you that a function is differentiable, which means you can find the derivative. I think I spelled it right.
Ow!
Okay, so you guys, I want to find out, when does the derivative fail to exist? We'll talk about differentiability implies local linearity. Derivatives on a calculator, we should know how to do that, but I can review it. It's up to you. And if you have a differentiable function, you have a continuous function. There's a theorem. You have to know that. Then we'll do this one tomorrow, intermediate value theorem, which we've done already, but we'll do again. Okay. And the reason why we care about derivatives is that when we graph differentiable functions, we can approximate it by their little tangent lines at points where the derivative exists. That's really important, because I might collect data just about the derivative and not know what the function is, but actually come up with a good picture of what the function might look like. That's a BC topic, but that's one direction you can go. The other thing is when you're calculating, and I've been told this maybe is not correct, when your calculators do calculations, like the tangent of 5 degrees or whatever, it actually does the derivative. It uses the tangent line to approximate that. The calculators are just that accurate that you come up with the answer. So it doesn't go through and do all the work, like e to the x, e to the 10th power. It's actually using the tangent line. It's a huge piece of BC calculus, approximating a function with just the tangent line. Well, our big focus is here, where do derivatives fail to exist? And I've seen this on the exam itself. And they're really these situations. The function will not have a derivative. That's where the slopes of the secant lines fail to approach that limit. Remember? The secant line is f of c plus h minus f of c. That's just the regular slope all over h. And it's where this secant line will actually approach a particular single value. So, where do we have problems? Sharp corners. Put simply, the slope on the left, because that is a limit, right, has to equal the slope on the right. It has to change nicely and smoothly and slowly, like going from reverse to forward in your car. You have to stop the car first. Otherwise, you have some problems. So this is a problem, because what's true about the slope on the left of the absolute value? Just look at the graph. What's the slope? -1. What's the slope on the right? 1. So if you were to tell me what the slope is at that point, you have to come up with a single answer, and some of you will say -1, some will say +1, some will say 0 because you average it. I can't even draw a tangent line. Did you zoom in on that in your lab? And you kept getting the V, didn't you? It didn't go away. You can't make it look like a straight line. That's the problem. A cusp is something that looks like this. This looks like a corner like that. I call it a sharp corner or cusp. On the exam, they won't care. You can say either one. And let's see, they have the square root of x. That function looks like this. Since I gave that as an example, let's draw it. The square root function looks like this. If I put that negative inside there, that just takes the square root of a -1 and makes it a +1. So that looks like that. So that's also a cusp. So to me, these are the same thing. I will not mark it wrong if you call it a sharp corner or cusp, and vice versa. Anytime we have a sharp turn, that's what the problem is. Vertical tangents. I want to extend my page so I can draw that better. And you ran into those too, didn't you? Yes? No? If I draw the cube root as best I can, it looks like this. and then it does this. And if I try to draw a tangent line at the origin, it's a vertical line. And what's true about the slope of a vertical line? It must be crooked. The slope of a vertical line is what? Undefined. So that all correlates to things you already knew. Vertical lines, you say no slope. I don't like no slope because it makes me think of zero slope. So I prefer to say that the slope of the vertical lines are defined. So I can't have a derivative if I have a vertical tangent. And I can even think of the example on the exam where they actually draw it in and they say, is this function differentiable? And they say it's a vertical tangent there. It's just that clear and that easy. Okay, so that's my cube root of x. Let me label that so it's not a problem. And number 4, we can go back to questions out of 3.1 because there were some questions there. A discontinuity, jump or vertical asymptote. Do you remember what this one looks like? The absolute value of x over x. If x is a positive number, then this is just 1. If x is a negative number, then this is negative 1. How can you find the derivative at 0? It doesn't even exist. You can't find a derivative at a point that's not even on the graph, right? Does that make sense? Forget that it's math class. Just say, does it logically make sense? It should. So those are the 4 things. Corners, cusp, basically the same thing. Vertical tangents, and any place there's a break in the graph, a discontinuity. So that's what 3.2 is about. So find all your points in the domain where the derivative does not exist. And I said, graph it on your calculator. I'm not even going to graph it on my calculator. We know what this looks like, don't we? Well, what's the parent function? What's the first function we're dealing with? Absolute value, right? Okay. What does the x minus 2 do to that function? Shifts it to the right. How many places? I know it's Thursday, but you got another day to go. 2, right? So this is going to come over to 2, and then what's it going to do? Up 3. And when I look at that, I actually see that picture in my head because I've done so many of these. Okay, where does the derivative not exist? F prime of x does not exist. Now it's asking where, which is the x coordinate. Where is that? At x equals 2. That's all there is. So if you have questions about it, graph the function. They're the basic functions you should be able to graph. This I would expect you to do without a calculator. The cube roots, probably that one too. Okay, these are just theorems. These are differentiable on their domains. Well, polynomials have a domain of everything, from negative infinity to infinity. They're differentiable everywhere. Rational functions, you remember what those look like? Looks like f of x over g of x, where f and g are polynomials. Remember what polynomials look like? Ax to the n, what kind of number does n have to be? Whole number. Can't even be a negative. Has to be a whole number. 1, 2, 3. It could be 0, by the way. Okay. Rational functions are differentiable everywhere except where what? G of x can't equal what? 0. It's a domain problem again. Domain is huge. The trig functions are differentiable everywhere as long as you're in the domain. Well, sine is easy. Cosine looks the same, so I'm not even going to draw it. But tangent has problems where it's not differentiable. And where, do you remember where those are? Pi over 2 and negative pi over 2. So that's the only problem with the trig functions. Notice it says in the domain. We've done this before. This is actually a review. Do you remember what a log function and an exponential function looks like? You need to know these poles. The exam will focus totally on e to the x and ln of x. I like to do the exponentials because they're easier. Maybe because we do them first. Remember what the exponential functions look like? That's y equals, I'll make it e to the x just so that we just start getting used to the e's. What is e? 2.71, who cares? It's a number. It's just a number. Like 2 to the x or 3 to the x. Okay, do you remember what the log function then looks like? It's the inverse, so reflect over y equals x. Now this domain on e to the x is the real. But what about on the log function? Y equals natural log of x. X has to be what? Greater than 0. But it's smooth. And by the way, if your function is smooth, no sharp turns or anything like that, that's nice and smooth. It's differentiable everywhere, and its derivative will be smooth as well. So I'm going to actually write that. If f of x is smooth, you know, it behaves nicely, no sharp corners, then f prime of x will be the same way. Whoops. Great. It's nice to know. Because some people will make them really sharp corners, and it won't be. If it was a smooth function to begin with no sharp corners, then the resultant won't be the same. I don't think it's smooth is the right word. Nope. Nope. If the derivative has sharp corners, its derivative will not be nice, but the original function might be a nice function. Yeah, that's backing it up in reverse is a little bit challenging sometimes, which is good. Now, then I have this little piece on your handout, and I took it off. It says about the linearity thing. What does it say? Let's just keep it simple. Part 2. If a function, and you have it written there, is differentiable, I'll just abbreviate that. Then you can zoom in. And what's going to happen to the function? F of x will look like a what? You take this curve here and I zoom it in, I get these closer and I go in closer and closer, it's going to look like a what? Will look like a straight line. Which means then that if I want to look here, I can approximate this function with a little tangent line. And I can go up here and approximate this function with a little tangent line. And I can do this all the way around, which is how your graphing calculators work. They just do the tangent line, because linear functions are easy, and then they put them all together. And we could talk about, like on the lab, what was the problem when you zoomed in on the vertical tangent? Anybody notice something interesting about that? When you kept zooming in on this piece right here? What did it end up looking like? It looked like there was a hole there, didn't it? Did you zoom in far enough to see that? Why does that happen? Because if this line is a vertical tangent there, then this would be a vertical line here. Can your calculator graph a vertical line? It can't. Why not? It's not a function. All your calculator can do is do functions. You can go into the draw menu. It will draw, it'll plot little points. So the calculator doesn't know what to do because it's zooming in and it's saying, this is vertical. I can't put anything there. I don't know how to draw that. Now, do you remember how to do this and derive? Do I need to review that? It is different with a different operating system. I'm not real good with the Inspire one, not having that work for me. Okay, I mean, you should make sure, because we're going to quiz you on this, make sure you know how to do this. Should we review it? I think we should review it. Homework quiz, and I don't know if it includes 2-4. For sure, 3-1. There it is. Now, unfortunately, this is going to be I'll do this first. The syntax, it'll be in the pretty print. But you have the older calculator. I'll get that. If you have the older calculator, you're going to actually type in Math 8. Oh, and there's the syntax. Yeah, I do have it on there. So it's n derived. And I like to put my function into y1. Because this isn't bad, but if you're talking about a rational function which has got fractions, and then the parentheses get pretty ugly. So if I do this, I have fewer problems with parentheses. And then it's x, comma. And what I could do, and it's at the value. It's called x. I think there's a short way to do this. Okay. And by the way, this is that graph from the homework. And I don't remember what number, 27 or something like that. Do you recognize this little graph right here? Since I have it here. I'd have to look in my book and see which one. If I go through here, I'm going to turn this off. It was x log x. We did it in the other class. Oh, wait. Turn it on. Graph. Oh, I turned off the wrong one. You know how to stop this. Just press on. Should work. Enter. Okay, turn off the derivative one. I don't want to see that one right now. Okay, there was a homework problem, and it was multiple choice. This is which one would be the derivative. They gave you the sine function. But the derivative of this looked like the sine function. Well, the answer is no, because I've got nothing to the left of nothing else. It doesn't even make sense. So by process of elimination, you should come up with the answer, which is the log function. But let's actually look at it. So y equals, and then I put the derivative in here, so let's graph that now. Yes? X is equal to x. I want it for all the x values. Let me drag this picture here, because you can see it better here. See, x equals x. That's pretty big. I don't know if I can do it better. And then we'll put the picture in. So there it is. And if you look at that new graph that's being traced out, it looks more like a log function. Look at your choices. The other choices don't even work. And I know that's what it is, because I know how to take the derivative of a log function. And what do you do when you multiply two functions together? How do you take a derivative there? It's coming on Tuesday. So that's the homework problem. So the answer is the log function on that one. Okay, so I want to go back to my graphic calculator. And we're going to put in, I have no idea, y equals, I'm going to clear this out. And what was it? X cubed? Okay, where is this guy? 3x to the fourth. 3x to the fourth. If it's negative. There we go. I'm going to do this problem right here. Review this. And it's plus 5x. You need a calculator. I have some. My calculator's disappeared, by the way, while I was gone on Tuesday. I don't know when. They were there on Monday. My 84s. Okay. I could graph the derivative. Should we graph it? Go ahead and graph the derivative? What do you expect? Not a bad exercise to do, but we could graph it, but I'm going to actually go in here and find the derivative. Oh, there's a couple ways you can do it. I can do math, now that I'm thinking about it. Go down to 8. Now, I don't want to go down to 8. I know it's at 8, so I'm going to press 8. And now, mine's not the old system, it's the new one. So this is the x that you put in that denominator. Because you have to talk about how something changes as something else changes. I don't want to type this whole thing back in here, so I'm going to pull it out of y1. It's under vars. You're going to want to be able to do that. Y variables. It's a function. It's y1. And then I want to do this for, what's my first value? -3. Now I have to have a negative sign. Negative's not forgiving if I do a subtraction sign. Yes. They look like this n derived. They'll look like that. But you'll still get the same thing. Now here's what I can do on the new operating system. On the old one, I can go second, enter. I didn't know this. And now I can go back and I can change that. And what was my next value? I'm going to move it over here. It was 0. So type in 0. Now, -0 shouldn't be a problem, but I'm not positive. Find out. There it is, 5. So I don't have to re-enter it. Now, if you're on the new one, you can just arrow up. Second entry is just as easy. Press enter. Well, you could do that before. Can't do that on 83. And I'm going to delete that, and I'm going to go back one more and put in 2. Oh, I was going to take pictures of these, but anyway, there it is. Maybe you want to look at the picture of the graph. It's up to you. Remember how to do that? Oh, could I read it off my graph? Sure. Now, the problem with reading it off my graph is that I have to have the right window. So I'm going to zoom 4, which is a decimal window, and I really only want from -3 to 2. Okay, I got a little problem here. I'm not seeing the whole picture. That's the problem. And I want it in my graph at -3. So let's see what happens. It's not going to be on my window, so I think I'm going to have issues. Second, calculate, and that's this dy dx thing, 6. And you tell it -3. Well, it gives me the value, I just can't see it. But if I'm, I don't know what the value is. I could zoom it decimal, standard. I don't think that's going to help me much. Nope, that's actually worse. But I got the value there. So let's do this again. Second, calculate. I at least have to have the x values. Let's do 0. Whoops. Oh, it's still thinking. Second, I don't know if this is going to work since I interrupted it. dy dx is 6. Okay, let's go back to zooming 4. Oh, wait, maybe we'll do it now. I don't know. Oh, there it is. It shows me right there. It says 5. But the thing is, you have to have the right window. That's up to you, which way you do it. I always do it under math. And the last thing is, if you have a differentiable function, it has to be continuous. This is the symbol for implies continuous. So what's going to happen on the exam? They're going to say to you, f of x is differentiable. They're not going to tell you it's continuous. You have to know that. And if you think about it, not memorize, if you want to be able to find a derivative, you better have the point on the graph. So it has to be continuous there. What about the reverse? We've asked this before. If f is continuous, so if they tell you have a continuous function, is it differentiable? Now, for that to be true, it must be true for every situation. If it's false, then give me a counterexample. That's the thing. Certainly continuous, but it's not differentiable. So, questions on homework, and we can go, 3-1 would be where, or even go back to 2-4 if you need to. So actually, I did one of those, and I'll tell you which one in a second. Tuesday, you should be done with 2-4 and 3-1. And you should be done with 3-2 so that you may ask me questions. So basically, I would say 2-4, 3-1 will be assessed on Tuesday. 3-2 should be completed by Tuesday. You see the difference there? So the one I just did, that was 24 with that funny little graph with the multiple choice. Nobody asked me questions about 23 except this morning. How about 23? Did you get that one? No, I didn't do 23. No, that's the rabbit problem. Rabbits and foxes. And by the way, that's what's going to happen on the exam. They're going to give you a problem with words, and you have to read a lot of words. Or what about 26? And what about 31? 26. This is the function. I want to make it look, I want to find the derivative. In fact, they even ask at what values, at what values of x between -4 and -6 is the function not differentiable. I was just toying with the idea of bringing up the PDF file, but I think it's just easier for me to graph it. So you're going to have to look in your book. I'll just do a quick little picture here. And they're all segments. We're back up to 2. Okay. Question B is easier to answer. At what values between -4 and 6, where is this function not differentiable? Now, if we just did today, this should be easy. Where is this not differentiable? Right. At x equals 0. Is that 1? I don't know. No, it's 1. And where's the other one? X equals 4. What's it? Differentiable every place else. Can I find the derivative anywhere on this line? Sure. Because what is the derivative? It's the slope. What's the slope of that line? Looks like it's 1/2 to me. What's the slope of this line? Negative. Well, it's 2 up and 2 down. It's only over 1, so it's -4. It looks like. Am I writing right on that? Just 1? Change of 1? Okay, and between 1 and 4, it's 0. And between 4 and 6, I'm going to go 2 on the x's, and I'm going to go up 4. What? No, I'm going up 4, and I'm going over 2, so it's 2. So then if I draw the picture of that on here, I have a slope of 1/2. This is at 2, okay? So 1/2 will be about here. I'll just draw it. And this was a -4. Leave an open circle there because I don't know what it is there. So this is going to go down to -4, which is going to be over here till I get here. And then I'm going to graph 0 from here to there. This is a different way of thinking, isn't it? And then I'm going to graph a slope of 2, which just looks like that. So should I highlight that? Because it's kind of hard to see. This piece, this piece, this piece, and that piece. That's the derivative. If it's curved, I got problems. And if this were on the exam, you would do it geometrically. You would not try to write the equation and use rules for derivatives. Other questions? 31 okay? Did you do 31? No? Did you bring your books? Let's bring your books. I have one book here. Should we look at 31? Okay. We did it in the other class. All we're saying on one side of derivatives is look from the left and look at the right. That's all. What we're going to do with this one is we're going to graph it. Because I know what it looks like. And I think it'll make it easier for you to understand the problem if I look at the picture. Using one-sided derivatives, show that the function does not have a derivative at x equals 1. That's misleading. Let's look at the picture. I don't like the way the author asked that question. Yeah, I'm not crazy with the book. Okay, so I'm going to put my graph here. I'm going to do the easy thing first. My split point, where I'm going to have issues, is at 1. Because this is a nice polynomial, x squared plus x. It's differentiable everywhere. 3x minus 2 is differentiable everywhere. So I only have to worry about what happens at 1. So at 1, what's the value of this function? I know it's not quite at 1. It's close enough, though, so I can still plot that point with an open circle. What's that getting close to? 1. So when x is 1, y is 1. And then I'm going to have a slope of, what's the slope of that? 3. So I'm going to go over 1, up 3. Pretty steep. That's what it looks over there. Clearly differentiable everywhere. Question? No? Okay. How do I graph the other one? Well, first off, we know what this looks like, don't we? What is that? That's a parabola. Now, I want to figure out how to graph the parabola, and I'm not allowed to graph in calculator, so I'm going to look for the zeros. So, when is y 0? When x is 0 or negative 1. It goes through 0. and it goes through -1, so it's a parabola. I don't really care exactly what it looks like. I just know it does this. What happens at 1? What's the value at 1? So f of 1 is equal to 2. Is that differentiable at 1? No. Not because of the derivatives. And if you look at this closely, what's true about those slopes? They look like they're the same, doesn't it? Does to me at least. If f of 1 is 2, and what's wrong with this side? It's the limit as x approaches 1 of my f of x. The limit isn't 2, the limit is 1. And remember, for continuity, that has to be true about f of 1 and the limit. For a function to be continuous, f of c has to equal the limit as x approaches c of f of x. Well, f of c was 2. This is 1. They're not the same, therefore it's not continuous. Can it be differentiable there? No. Does it have anything to do with one side, left, right, and left sided derivatives? Not really. It's not even continuous, so we don't have to go there. But let's go there anyway. Yeah, let's go there anyway, because we can do this quickly and easily, and if we cheat a little, we can really do it easily. What's the slope on this side? 3. Now, does anybody know the easy way to get the derivative of this? What is it going to be? 2x plus 1. You've got to come on Tuesday to find out why. Some of you have figured it out. Okay, what is the value of changing? That's why this is a function. What's the value of that at 1? So m equals 3. So the slopes are the same. So if you, in fact, I think when I did the problem, I went in and found the slopes, and I said, oh, it is differentiable there. No, it's not, because it's not continuous. So it's a misleading question. They should have just said, is it differentiable here? And let you look at it. And the first thing I would check is it even continuous? Because if it's not, I'm done. If you were on the exam, they might say show, whatever. Because last year I know you had to make the statement that FC was not equal to the limit. I can bring that problem up. If I remember to bring it up, I can bring it up tomorrow, actually. That'd be a nice little problem to do. So, and then we did 40 and 41, which were similar, because Sasha asked that question yesterday. And I don't know what else there is that you would question. Or is that it? Because you have some time to work. You've got 20 minutes that you can work. But you need a book. Tomorrow we'll do the intermediate value theorem, and we don't have to do much with it. I don't even like their example on that. So I might not even worry about it.